Hello everyone. In this video we're going to look at limits at infinity, which means x approaches infinity or negative infinity. Okay, so what we're looking at here are rational functions. So they're a fraction of polynomials. And what we do to solve these problems is we look at the denominator, and out of the denominator, we look at the term with the highest degree. So that would be this x here, degree 1. And we divide by that power. So here we have the x has the highest degree, and so I'm going to divide by x. And you do that to the numerator and denominator. X is approaching infinity, so x is not equal to 0. And then you divide you multiply the numerator and the denominator by the same expression, 1 over x, so it's like multiplying by 1. And then we use the distributive property through, so we'll get limit x approaches infinity. And usually I don't show quite all this work, but you could write 3x times 1 over x minus 1 times 1 over x. It's obviously going to go faster if you do that in your head, which is, I think, within a reasonable thing to do. So you might just ignore this step and you go right to this, but I'll just show that just to make it clear. What's going on is that I'm using the distributive property, multiplying each of these, and and so, but I think a bit of those you can do in your head, right? And then the upshot of this, or what's going on, is that then we look at these pieces here, 1 over x and 5 over x have a limit of 0. Why is that? Because x is approaching infinity. So infinity is not a number. X is becoming very, very large without bound. So you have 1 over a very large number. It doesn't equal 0. The limit equals 0. It approaches 0, infinitely close to 0. And so therefore, using limit laws, we would have 3 minus 0 divided by 2 plus 0, and that makes 3 halves. And so that's our answer there, and I'll just do some other problems that really follow along with those same ideas. So also, what this means is that if you looked at this function here, y equals 3x minus 1 over 2x plus 5, this function has a horizontal asymptote, which is y equals 3 halves. And so that's something that's a pretty standard idea from a pre-calc class, is that if you have a rational function, the degree of the numerator and the denominator are both the same. In this case, they're both degree 1 for numerator and denominator. Then you look at those coefficients, 3 over 2, and that gives the horizontal asymptote. But here I'm trying to explain the reasoning behind that, how we got to that point where you can just look at the coefficients of x, or the coefficients, sorry, of the highest degree term. So for this next one, we look at the denominator and we see that the highest degree term is x squared, and so I multiply by 1 over x squared on the numerator and the denominator. And this time I'll go a little bit quicker with applying this 1 over x times 3x, 1 over x squared times 1. So this makes 3 over x minus 1 over x squared. All right, so once again, I'm distributing and multiplying those. On the denominator, 1 over x squared times x squared makes 1. Then 1 over x squared times x makes 1 over x. 1 over x squared times 1 makes 1 over x squared. These pieces here, those have limit 0. In fact, everything has a limit 0 except this 1 here. So this gives 0 minus 0 on the numerator, 1 plus 0 plus 0 on the denominator. That's 0 over 1, and that equals 0. This fits into look at a rule where if you have a rational function, if we look at a rational function, and the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0 to the x-axis. So that's a rule of rational functions. The degree of the numerator is less than the degree of the denominator. As x goes to infinity, we get limit 0, which means there's a horizontal asymptote, y equals 0. In this next problem, the degree of the numerator is greater than the degree of the denominator. We'll see that that leads to either an infinite limit, either negative infinity or positive infinity. And so I look at the highest degree term of the denominator, and that's x. So I'm going to divide by 1 over x. I'm going to divide by x. So I have 1 over x in the numerator, 1 over x in the denominator. I will distribute that throughout. So I'm going to get limit x approaches negative infinity. 1 over x times 3x squared makes 3x. And then we have x times 1 over x makes 1. Negative 1 times 1 over x. It's 1 over x. Etc. 2x times 1 over x makes 2. 1 times 1 over x makes 1 over x. Okay, let's check this out. So 1 over x is limit 0. 1 over x is limit 0. 3x has limit negative infinity. X is approaching negative infinity. We multiply by 3. Still be a negative. So this is negative infinity. So this guy, the denominator in total is going to 2. I mean, I was writing arrow goes to 2, but it's not, it's the denominator is 2, the numerator is going to negative infinity, so we get negative infinity. So this is the situation where the degree of the numerator is greater than the degree of the denominator. In a, if you're getting more into sketching this graph, you can do long division, and you'd see that this is a you would result in a line. If you do long division, you'll get a line plus a number over divided by 2x plus 1, and that will give us a oblique asymptote, but still the limit's negative infinity. So that's another topic, of oblique asymptotes. Over here, we have a similar situation where we, we look at the denominator, and we see that the highest degree term is x. So I'm going to multiply by 1 over x. And same in the numerator. Now we use a fact. If x is greater than 0, then square root of x squared is equal to x. All right? So this guy over here then, this 1 over x, can be expressed as the square root of 1 over x squared. Because x is positive, those are the same thing. So then you need to do that. We're going to use the fact that the square root of a times square root of b equals square root of ab. So see, I have this multiplication here of two radicals, and because they're both under radical square root, when I multiply, I can put them all under the same little house of radicals, little building there. So see there, I'm multiplying that, so I'm going to get 9x squared plus 1 times 1 over x squared. And then the denominator is, I just distribute 2x times 1 over x, 3 times 1 over x. So that gets 2 plus 3 over x. Simplifying more, the square root, 9x squared times 1 over x squared is 9. 1 times 1 over x squared is 1 over x squared. Zero, 0. So we get square root of 9 over 2, which is 3 halves. All right. There's another way of looking at this. It's quite a bit of a shortcut. The shortcut for all of these problems could be, it works, absolutely works. when you look at x goes to infinity and you have a polynomial, you can ignore all the lower degree terms. You just look at the highest degree terms. As x goes to infinity for a polynomial, you focus on the highest degree term, and that gives the infinite limit. So if you do that, that means you could just look at radical 9x squared divided by 2x. That simplifies to 3/2. You could do that for all of those. However, there is, let's see if we can try this for the next one. The next one is sort of like a bonus and sort of optional. I feel like to complete this video, I should do this. We're going to write down the exact same problem. This time x approaches negative infinity. And this is going to be like more difficult than all others, as the 4 before combined. Okay, look, let's talk about whether our answer will be positive or negative. The numerator is a square root, and a square root is never negative. It could be 0, never negative. The denominator has 2x plus 3. When x becomes a large number, the highest degree term 2x dominates. So as x approaches negative infinity, we look at the 2x, and 2x will become a large negative. I mean, you could just put in negative 100. 2 times negative 100 plus 3 is negative. So the denominator is getting to be a large negative. The numerator is a large positive. Positive divided negative, whatever our answer is, it's going to be negative. I guess it's going to be negative 3/2, but it's going to be a negative. The denominator is becoming is a large negative. I mean, you can just put in negative 10 and the denominator is negative, and the numerator is positive. So it's going to be negative. All right. So let's see if we can model our way through this. So, okay. So I'm going to just rewrite this. X approaches negative infinity. 2x plus 3. Then I have 9x squared plus 1. All right. I want to divide the numerator by 1 over x. Or the denominator by 1 over x, because that's the highest degree term in the denominator. All right. If I do that for the numerator, okay, so far so good. But now what I have to do is use this fact. Okay. If x is less than 0, this is the key here. If x is less than 0, the square root of x squared is equal to opposite of x. So for an example, x, say, is negative 5, which is less than 0. The square root of negative 5 squared is the square root of 25, which is 5, which is opposite of negative 5. See, it's sort of confusing. In general, the square root of x squared is equal to absolute value of x. That's the general idea. But for this one, when I multiply this here, what I'm saying here is that the square root of x squared is equal to negative x, which is the same thing as, or multiplying by both sides by negative 1, negative radical x squared is equal to x. See, so then if I replace, what I'm going to do is replace this 1 over x by negative radical 1 over x squared. My notation might be not so good, so let's put parentheses like that. I could see someone saying, no, I have a faster way, a better way to do this. But what I'm doing is, it's going to give the right answer. I'd be interested, need to study more. What are other people doing? Okay. I think this is it. So when I simplify this, I'll put the negative in front. Radical 9x squared plus 1. And then I have them both under radicals, so I multiply by 1 over x squared. distribute the denominator 2 plus 1 over x. So this is a situation where x is approaching negative infinity. That's the key, and maybe I didn't make that clear. See, I said when x is less than 0. The reason x is less than 0 is because x is approaching negative infinity. So 1 over x is equal to negative radical 1 over x squared. Just keep in mind that a radical is never negative, but 1 over x is certainly negative because x is approaching negative infinity. So it would have to be negative, the radical. 1 over x is negative. It has to be negative of the radical because the radical is positive or 0. So that's the one way to look at it. And then 1 over x, get to this point, 1 over x is limit 0, 1 over x squared is limit 0. So we get negative radical 9 plus 0 over 2 plus 0. Seems the handwriting here is deteriorating along with my pen for some reason. Okay. So this is going to give negative radical 9 over 2, which is negative 3/2. If we looked at this in terms of graphing the function, this function, which I have for both 4 and 5, same function, has limit. This function has limit as x goes to infinity, 3/2, but as x goes to negative infinity, negative 3/2. So you can think in terms of horizontal asymptotes, y equals 3/2 to the right, and y equals negative 3/2 to the left. Okay, so last one was definitely something difficult, a little bit difficult. And this is, all this stuff over here is supposed to be sort of side work. Same with this right here. Okay, it looks a little messy though. Alrighty, that's all for this video.